5.2, damped motion. Damped motion. What does damped motion means? Does anyone has any idea what that means? What's damping? So it's important to know what that means. Damping, it's kind of like has to do with reducing or preventing, let's say, oscillations. That's what damping means, or damping force. Can someone give me an example from real life situation? So someone is saying friction. Other examples? How about electric currents? Noise in general? Shock observers, right? There's a lot from real life. That's what damping means. So damping motion, damping force, it's gonna be reducing oscillations. What's the idea here? Idea behind this section? What do we have? So let's say we have a spring with a mass attached to it. Okay, a mass attached to it. But this mass is inside, say like that. There's like water in here. Goes inside the water. So this is mass. This is water, H2O, water. So what's happening when you try to pull it down and let it go? So what's happening here? The motion of the mass goes through some kind of damped force, such as this one that you see on the right side. So I can write that down. The motion of the mass goes through some kind of damped force, such as this one. So in this case, we say motion is damped. Motion is damped. And what we have here in this section is that damping force is always going to be proportional to the power of instantaneous velocity. So this means the force is going to be constant, some constant times the multiple of dx dt. That's what the instantaneous velocity is going to be. So it's proportional, means there's a constant. Provided there's no other forces acting on the system. For now, maybe you're like, what's happening here? You'll get the big picture later on. Now we can do Newton's second law. We can use that to write down a differential equation to model that thing. md square x dt square negative kx. That's coming from this part. Not this part, the next one. Negative beta dx dt. And those negatives, they came from the fact about the opposite to the motion or something like that. What is beta here? Beta is called the positive. It's a positive damping constant. If we take that differential equation and divide by m throughout, you get d squared x dt squared equals negative k over mx minus beta over m dx dt. We're interested to learn how to solve such equation. To do that, let's move everything to one side. D squared x dt squared plus beta over m dx dt plus k over m x equals to 0. But for simplicity, I'm going to rewrite this as, instead of beta over m, I'm going to call it 2 lambda dx dt, and instead of k over m, we're going to call it omega square x, as we did in the previous section. So we can say where 2 lambda is beta over m and omega square is k over m. So then, if you want to get the characteristic equation of that, you get m squared plus 2 lambda m plus omega squared equals 0. That's the characteristic equation. And if we want to solve this, we can use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. We may take a 4 out as a 2 from inside the radical and divide top and bottom by 2. Negative lambda plus or minus the square root of lambda squared minus omega squared. So that means there are two solutions here. One solution, m1 equals negative lambda plus the square of lambda squared minus omega squared, or m2 is negative lambda minus the square root of lambda squared minus omega squared. Now, when we get to this point, remember we're trying to solve that differential equation, which modeled that situation for us. We're about the damping force or damping motion. When it comes to this point, it all depends on what's inside the radical. Is that positive, 0, or negative? So that will tell us that we have 3 cases to deal with. Case 1. I'm going to take the fact that that part is bigger than 0. And always, if that's bigger than 0, it's always said that the system is set to be overdamped. And in this case, if we want to solve the equation, the differential equation from before, remember C1e m1t plus C2e m2t, they are distinct roots. For this works for real roots. And remember, what is m1? So you can rewrite this, C1e. m1 is negative lambda plus the square root of lambda squared minus omega squared t plus C2e negative lambda minus the square root of lambda squared minus omega squared t. That's the solution for that equation in case the quantity inside the radical is positive. Now, if you look at probably in the textbook or some other books or in the back of the book maybe, let me show you something. Sometimes you might see a different form of this. If you can break out this as e to the negative lambda times the square root of lambda squared minus omega squared t plus C2e negative lambda times e negative the square root of lambda squared minus omega squared t. Then what we have out, and why did I do this? Because now you can factor out e negative. You can put the t here if you like, and same thing for the other one. Put the t there. You can take e negative lambda t out. C1 e the square root of omega square lambda square minus omega square plus C2e this negative omega square lambda square minus omega square. See, there should be a t here because you distribute the t in. Same thing there, so don't forget those. And the t is outside the radical. Keep that in mind. Note, so again, this is just another form. Note that beta, the damping constant, is way bigger than the K, which is the spring constant. So what happened in this case, in this specific case, which we called it over damping, what happens is, if you want to look at it graphically, this is the t-axis, that's the x-axis, basically x of t, or x, like that. So what happened is this is the motion. What happened? So as it keeps going in motion, like so, it's gonna go down, 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 and eventually it's gonna die. So that's what this over damping means. Over damping means at some point there's going to be no oscillation at all, and it's going to just flat down to zero. That's the first case. Case 2. How about if the quantity inside the radical is 0? In this case, the system is called critically damped. Okay, and in this case we have like double roots, like the roots are the same. So m1 equals m2 equals, if you look back at the equation from the quadratic formula, if this is 0, then m will be negative lambda. So both m1 and m2 will be negative lambda. Okay, so now the solution to this x of t is going to be e negative lambda t, as I did earlier, c1 plus c2t. That's the solution for this. Now graphically on the right side, it's going to go down and then barely oscillate and goes down again this way. So it looks like almost wants to start oscillating. So that's called critically damped. So it's called critically damped since any decrease in the damping force will give some oscillating motion or oscillatory motion. That's what this case is about. So as I said, this graph will, or shows that it looks like almost wants to start oscillating. Case 3. How about lambda squared minus omega squared less than 0? So that means there's complex numbers involved. And this roots would be, if you go back and pull the negative out, it would be plus or minus the square root of omega squared minus lambda squared I. And in this case, the roots would be, or the solution, lambda t times c1 cosine omega squared minus lambda squared t plus c2 sine omega squared minus t lambda squared t. That would be the solution. And in this case, it is called, like the system called, under damped. So how does that look like on the graph? Again, t and x of t. So it's gonna come down from somewhere like this, and then up, down, up, and eventually it goes to 0. And you can see this here. If you look at this term there, from this term, as t goes to infinity, like t gets bigger and bigger, then e negative lambda t goes to 0, and hence that tells us x of t also goes to 0. That's why it flats out. So 3 cases. The first case, there's almost no oscillation. Second case, looks like it's gonna start oscillating. And the third one, there is some, but eventually it's gonna go to 0. Now keep in mind, the equation we just wrote today, the differential equation, takes this form: mx w prime plus beta x prime plus kx. So if it takes this form, then it is a damped motion, like means we are working in this section. We are in this section. But if the beta x prime term is 0, then it is a simple harmonic motion. Wait. Yeah, harmonic motion. That's the previous section. That's the difference between the previous section and this section. So we are wanting to learn how to solve this kind of differential equations. Let's look at this one: xw prime plus 5x prime plus 4x equals 0. X prime means dx dt or dx or dy dx, some kind of differential form, with the initial conditions x of 0 is 1 and x prime of 0 is 1 as well. So we need to solve such differential equation. To start solving such an equation, we find the characteristic equation from this, which is m squared plus 5m plus 4 equals to 0. Easy to factor: m plus 4, m plus 1 equals to 0. And that would give us m equals -4 or m equals -1. So that's the first case, overdamped case. If we want to find the solution, you look back at the formula. It says C1e m1 t plus C2e -t. Now they give us initial conditions, so we need to use both of them. So x of 0 is 1, C1e to the 0 plus C2e to the 0. So that gives me an equation: 1 equals C1 plus C2. And x prime of t, -4 C1e -4t minus C2e -t. So x prime of 0 is -4 C1 minus C2 equals 1. So we got another equation. Solve for C1 and C2. I got C1 -2/3 and C2 5/3. So then I can go back and replace these two in the boxed form, or that equation. So we get x of t, C1 is -2/3 e to the -4t plus 5/3 e to the -t. This is the final equation. So this is just to interpret this. This is an overdamped motion, as I said, with the mass on the spring, which starts like 1 unit below the equilibrium case or equilibrium level, with downward velocity of 1 unit. Now, one thing I would recommend you can do, use Desmos. Note, use Desmos to sketch a graph for this solution, and you will see, as soon as like y equal that, and you will see that it doesn't oscillate almost at all. Another thing I want to ask what would be the maximum displacement if we're asked from this motion. Well, maximum displacement means we need to find the derivative and set it equal to 0. So I take x prime, which is negative 2/3 times negative 4, that's 8/3 e to the negative 4t, minus 5/3 e to the negative t. And you set it equal 0, you can factor e to the negative 4t out, and also 3. You get 8 minus 5 e to the 3t. And in order for this to be 0, this cannot be 0. So only 8 minus 5 e to the 3t must equal 0. So solve for t now by subtracting 8, divide 8/3, and then do natural log both sides. So 3t ln of e is 1, is natural log of 8/3. So t equals natural log of 8/3 divided by 3, which gives about 0.157. Can the, if I want to call it part B, when does this go through an equilibrium? Equilibrium, so when does it go through equilibrium? Equilibrium, that's when x of t is 0.
Wait, well, Professor?
Yes.
In A, what happened to the 5?
Let me see. Oh, I thought it's 3. It's 5 here. Yeah, 5. Confused between the 3 on the top and the other one.
Okay, yeah. Thank you.
So when does it go through the equilibrium? That's equilibrium when x of t is 0. And if you look at x of t, the one we got, what was x of t? See, it's a combination of a linear combination of two exponential functions, which will never be 0, because the first one will never 0, the second number never 0, their sum will never be 0. So this is impossible to happen. Impossible to reach an equilibrium position. Next example, as an application from the book, let's say an 8-pound weight stretches spring 2 feet with a damping force, this is all given, equal twice the instantaneous velocity. We would like to find the equation of motion if released. So when you release the weight from the equilibrium with upward velocity of 3 feet per second. So they want us to find equation, right? So this is how I think about it. What is the formula? What's the formula for the equation for the damped force? Is mx double prime plus beta x prime plus kx equals 0. So again, to find the equation, they ask us to find the equation like this, and we're going to solve it. Okay, we're going to solve it. So to do so, we need to find m, beta, and k. M, beta, and k. So let's start to find k. K is the spring constant. We learned in the previous section that F equals Ks. The force they give us is 8 pounds. We're looking for K, and S is 2 feet. from the first line of the problem. So K is 4. I got K. Now how do you find the mass? Weight equals mass times gravity. The weight is again 8 pounds. We need the mass, and the gravity is 32. So then the mass is 8 over 32, 1/4. Slug. Here, what else we need? We found these ones, and beta, we found M and F, or K, sorry. We need beta. Beta, because it says the damping force is twice. This twice means beta. That's beta. Beta is 2. So we found them. Now they give us more information here about the 3 feet per second. So the first thing, the motion released from equilibrium. From the equilibrium, that's when x of 0 is 0. That's the equilibrium position. And they give us with an upward velocity. Upward means in the negative direction. So means x prime of 0. That's what velocity x prime at 0 is -3. That's called the initial velocity. So I found from the given problem, I analyzed the given. I was able to solve for K, for M, and for beta, and produce the 2 initial conditions. So M is 1/4, so 1/4 x double prime. Beta is 2x prime, and K is 4x equals to 0. Multiply everything by 4, so x double prime plus 8x prime plus 16x equals to 0. Then the characteristic equation becomes m squared plus 8m plus 16 equals to 0, which gives us m equals m plus 4 squared, so m equals -4 or -4 repeated roots. So then the solution to this would be x of t equals c1 e -4t plus c2 t e -4t, because it's repeated. But they give us some conditions. X of 0 is 0. What do we get out of this? C1 plus 0 equals 0. So C1 is 0. And x prime, so we need to find x prime, which is -4 C1 e -4t minus, actually plus, there's a product rule there, C2 times 1 e -4t minus 4 C2 t e -4t. So substitute the 0 in, x prime of 0, that's a -4 C1 plus C2, and the last one is 0 equals -3. But C1 is 0, so that gives me C2 -3. Then I substitute them back into x of t. So the solution would be C1 is gone, C2 is -3, t e -4t. That's the solution. And you may graph it and see how the graph is going to look like. This is a duplicated root, so you expect the graph to oscillate a little bit. That was the second case. Now for underdamped motions, if you remember from previous section, and I'll come back to this in a minute, AE -t sine omega t plus phi. If you remember, this had a period of 2 pi over omega, and this part here is called the damped amplitude. I'll come back to this in a minute. Okay, so let's look at this equation. Given 1/2 d square x dt square equals -5x minus dx dt. Given x of 0 is -2, x prime of 0 is 0 with the initial conditions. So I'm going to try to solve this and come back to it and comment on it. Okay, I'm going to use it. The idea behind this is to see an alternative solution to this, or alternative form of the solution. So what do we do here? We can multiply everything by 2 first and rewrite this for simplicity. X double prime negative 10x minus 2x prime. So x double prime plus 2x prime plus 10x equals to 0. And we can get the characteristic equation of this, which is m squared plus 2m plus 10 equals 0. Solving this using quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a gives us negative 2 plus or minus negative 36 over 2. So m equals negative 2 plus or minus 6i over 2. That gives negative 1 plus or minus 3i. So we have two complex roots, negative 1 plus 3i, and the other one is negative 1 minus 3i. So now, after we found the roots, we can find x of t. This is the third case. E negative lambda t, lambda is 1, let's say, t times c1 cosine. If you look at the formula, the square root of omega square minus lambda square, that's 3, because everything went down to 3. 3t plus c2 sine 3t. Now, from the given conditions, from the given initial conditions, what we can do, we can solve and get c1 as I did, negative 2 and c2 negative 2/3. I'm sure everyone knows how to solve this. Then x of t becomes, if you substitute them now in, negative 2 cosine 3t minus 2/3 sine 3t. Okay, so now we recall from the previous section that x of t, which is the one was for this case, c1 cosine square root of omega square minus lambda square t plus c2 sine the square root of omega square minus lambda t has alternative form x of t equals a e negative lambda t sine the square root of omega square minus lambda square t plus phi. That's the alternative form. So whatever solution I just got in the box, we can rewrite it like this. We can rewrite it with this form. That's just an alternative form for the solution. Phi here, if you remember, called phase shift. And to solve for phi, if you guys remember, we do tan inverse c1 over c2. And to solve for a is the square root of c1 square plus c2 square. All this from the previous section. So this part here again is called damped amplitude. So back to that example, revisiting, the x double prime plus 2x prime plus 10x, the one we just did, equals 0 with the initial conditions, x of 0, negative 2, and x prime was 0, 0. So we can ask you find the alternative form for the solutions for this given differential equation. Of course, to do that, We need omegas, we need like, or phi, we need A, we need lambda. So to find A, we already had C1. Remember, C1 square plus C2 square that we found earlier in the previous solution. C1 was -2 square, and the other one -2/3 square. That's a 4 plus 4 over 9. Take a 4 out as a 2 and a 9, 3. That will leave 1 plus 9, 10. 2/3 the square root of 10. To find phi, you do tan inverse of C1 over C2. Tan inverse of -2 over -2/3. Tan inverse of 3. If you put in the calculator, I got 1.249 radians. But remember, these two c's both are negative. So this means phi must be located in the third quadrant. So what do we do here to find exactly what phi is the number I just got, 1.249, plus you add pi to it. Add pi. That gives 4.391 radians. That's phi. And I found A. What is lambda here? Do you guys remember? What is lambda? And also we need to find omega square minus lambda square. What is lambda? So from the solutions, lambda is 1. How about omega square minus lambda square? What was it? It was 3. Yeah, good job. It was 3. So we got lambda and this. Now the alternative solution to this, x of t, we're looking for is a e negative t, or negative lambda t, if you'd like to put that in, times sine the square root of omega square minus lambda square t plus phi. And to do that, so you got A is, we found it 2/3 square root of 10, e negative t, because lambda is 1, sine. This one we found is 3, so 3t plus phi was 4.391. This would be the answer. Anyone has any questions about this?